This is Physics Review video number 1, and this is focusing on describing nature, observations, measurement, and analysis. We'll cover observation, measurement, specifically expressing numbers in scientific notation and using metric prefixes, metric estimation, vectors, and looking at patterns and relationships. Physics is all about describing nature, and we want to see the cool stuff. So this is a simple Newton's cradle. And we're just thinking about what can we observe about this system and what can we actually measure about this system. Well, we observe that the person pulls back one ball, so it changes the position of one ball. We can measure the time it takes for it to change position. We can measure the time it takes for any of the balls really to change position. With a stopwatch, we can measure position with a meter stick. We can measure angle with a protractor. And a lot of times my students will say, oh, well, we can measure speed. Speed is difficult to measure directly, but we can certainly look at the position measured with a ruler and the time measured with a stopwatch and track how quickly the object changes position with time to determine speed. So these are some of the things that we might want to measure. However, when we think about position, we have to think about, okay, well, with respect to where's our 0 mark we might put, or our coordinate system. Then we also want to think about direction, what direction it changes, and we also want to come up with a common language for this scaling. So how long is this? Is it my finger? Is it some standard measure, like a centimeter? Or we'll use the unit of meters in this class. So we can express numbers in different ways. For example, we might see that a number is expressed as 32 centimeters. Well, centi is a prefix before our base unit of meters, and we always want to get our numbers into base units, either meters, kilograms, or seconds. And that's kind of special, not super special, but special for physics. So centi, if we look in our reference table on the front page, actually is a prefix that means 10 to the negative 2 meters. So really we have 32 times 10 to the negative 2 meters. And 10 to the negative 2 really just says take wherever the decimal is and move it over to the left 2 times. So 32 centimeters is 0.32 meters. Or if we wanted it in proper scientific notation, which we might see it in someday, we would have it as 3.2 because that is our coefficient between 0 and 1 times 10 to the negative 1 meters. Another example shows instead of a spelled out prefix like centi, just a symbol for the prefix, which in this case is kilo. So I'll change colors here. If we look up kilo, kilo means 10 to the 3 meters. So putting it together, we have 1.47 times 10 to the 3 meters. And so that's 1,470 meters. Because the 10 to the positive 3 means take wherever the decimal is and move it to the right that number of times. We also want to get things from kilograms to grams or grams to kilograms, and that's a little bit different of a process than from kilometers to meters. So we can look at that by really thinking, okay, well, I have 89 grams. Well, that's less than 1 kilogram. So I better get something that's a decimal. Well, I want it in kilograms. So that's 10 to the 3 grams, really. So I want to know what 89 out of 10 to the 3 grams is. So 89 grams out of 1,000 gets us into the kilogram unit, which is 0.089 kilograms. Another way sometimes people will think about this is it's 10 to the 3 decimal places, or just 3 decimal places different. So if my decimal was here, I would actually move my decimal to the left to kind of get to a larger unit. You would move it to the left, so 0.089 kilograms. We'll see all sorts of numbers in scientific notation. For example, on the first page of the reference tables, we have the universal gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. This is a super small number. This highlights the advantage of scientific notation. No one wants to write 10 zeros in front of this 6 and then a decimal after that and think about that number in its full long standard notation form. So scientific notation is really useful in this way. In your calculator, if you were to type this in, you would type it in as 6.67 e negative 11. And your calculator might spit out an answer with this e notation here. E just means times 10 to. And then that power is what goes here. So that's another way to help use your resources, your calculator, to understand and be able to translate between scientific notation and standard notation. So we might want to estimate just to make sure we're on the right track with some of our calculations, or be able to recognize what different sizes are in this metric system. So some good things to memorize in terms of metric estimation is that 1 meter is approximately 3 feet. 100 meters is a football field or a soccer field. 1 story is 3 meters or about 10 feet. The average student is 70 kilograms. 1 kilogram is 2.2 pounds, which is about a big, good textbook. And a gram is about a paperclip. And a meter per second is walking pace. So you might get a question like, a 3-story building is approximately how many meters tall? Well, I know that 1 story is approximately 10 feet or 3 meters. So I can determine how tall a 3-story building is by taking that 3-story building and multiplying it by the number of meters per story, 3 meters per story. So I end up with 9 meters. And a lot of the times questions like this have a power of 10 as their choices. So 9 meters is approximately 10 to the 1 meters. So that's a way to do a metric estimation question. Think about what you already know in that problem and see if it's reasonable. Now, an answer like 10 to the negative 2 meters is unreasonable. We know that this is smaller than 1 meter, and buildings are bigger than that. An answer like 10 to the 6 meters is also unreasonable for the opposite reason. That's really, really, really large. It's 1,000,000 meters. So that's what estimation is really all about, getting close without getting kind of bogged down in the specifics. Our measurements can come in just numbers, like with metric estimation, but also when we were looking at this video, we thought about direction and coordinate and how was it pulled back, and okay, so well, the ball was pulled back to the right, and when I let go of it, it swung to the left, and then it hit the balls, and the ball on the far left swung. There's a lot of direction in there, and direction is important when describing nature. The things that we call vectors, these things we call vectors, are really just categories of descriptors that include direction. So something we might describe as a vector is velocity. Well, velocity is a certain amount of speed, like 10 meters per second, but in a given direction. And it really matters which direction your velocity is in. Is it off a cliff, or is it onto safety? So vectors are required if we want to give an accurate, thorough description of whatever phenomenon we're seeking to understand. So we need an origin, we need a starting point to determine, what is left and what is right, what is up and what is down. Often we will call up positive, we will call down negative, we will call to the right positive, we will call to the left negative, just like your typical mathematical coordinate, two-dimensional coordinate plane. Now, really, directions can be 3 dimensions, right? We live in a 3-dimensional universe, so there is even further need for vectors and their descriptors. We might have a plane flying in a certain direction or a drone flying in a certain direction, but the wind pushes in another direction. Well, we need to know where that plane is going to go. And we can see how that plane is going to act based on the influence of these two forces, or these two directions that the wind and the actual propeller are pushing, by creating this parallelogram sort of thing. So if you put the vectors tip to tail like this, you can create the resultant that way. But also, if you put them tail to tail and make a parallelogram out of it, the bisector of that parallelogram is the resultant here. So just looking at, if I push this way with some amount of force and I push this way with some amount of force, the resultant force would actually be in this middle direction. Well, if I have a vector that's off in some direction that's not just horizontal or not just vertical, I need to understand the ball's motion both in the horizontal direction, which is not affected by gravity, and the vertical direction, which is affected by gravity. So I really need to break up this vector, the velocity vector, into a horizontal component and a vertical component. Well, I can do that using these equations on the reference tables in simple right triangle trigonometry, because the adjacent side here can be calculated through the hypotenuse v times cosine of the angle theta here. And the opposite side, the vertical side, is the same kind of way, hypotenuse times sine theta. So we have this need to understand the influence of these directions separately, so we have to take into account direction, and sometimes we need to even decompose those directions into a completely horizontal or a completely vertical direction, or any really direction. So once we have our measurements and our observations, we need to seek some understanding. In some ways, common ways that we in physics use to understand phenomena are patterns, relationships, and graphs. The most common one that we'll see probably is a direct pattern or a linear pattern. So as one function increases, the other function increases in an equal amount, or as one function decreases, the other decreases in an equal amount, an indirect pattern. One example of that is the force on a spring compared to how far it's stretched. A direct squared pattern is when it grows kind of at an increasing rate. And for one change in the x value, you get that same change squared in the y value. So instead of increasing at this constant rate, it increases at a growing rate. One example of a relationship that's like that is the centripetal acceleration formula. So centripetal acceleration equals v squared over r. So how is centripetal acceleration related to v? Well, v is squared in this relationship, so it's related to v squared. The inverse pattern is another one we'll see, where if something is really small, for example, the mass of a system is small, then the acceleration is going to be large depending on the force. And the inverse squared function, for example, the force of gravity between two masses is inversely proportional to the distance between the two masses squared. So we can see that reflected in the 1 over r squared relationship here, which we'll see a lot more. Hope you enjoyed this video. Tune in for the next one.